now, actually.
Oh.
So, equivalents per liter. All right, so looking ahead, chapter 6 quiz is due Sunday in the discussion. And quiz, by quiz I mean homework questions, sorry. Shouldn't say quiz, that scares people. Discussion.
Good morning.
Good morning. And then chapter 7, the following. Oh, big one, info lit paper. Remember, it's we're 10% of your grade, same amount as an exam, so you really want to try hard on that. And just email me if you can't find an ingredient, anything like that. I can usually help you figure out whether it's the purpose or you need a structure, or I can give you an alternate name that'll help you find it easier, anything like that. So what we're going to look at first is this number 19. So I didn't cover it in the last chapter lecture video, but it is a concentration. It is a chapter 6 problem. So what it is asking is the equivalents per liter. So I talk about it a lot in the PowerPoint, but I didn't actually show a problem on it. Equivalent per liter. That's what this EQ/L means. So when you're trying to solve for equivalents per liter, what you're doing is you're taking the magnitude of the charge on the ion and multiplying it by the molarity. So this is why it's a concentration problem, is because we're multiplying it by molarity, molarity being a concentration. That's that moles per liter that we did calculations with last lecture. So what do I mean by magnitude of the charge on the ion? Okay. So when I say magnitude, what I'm telling you is the number of the charge, not the actual sign of the charge. So it doesn't matter if it's negative or positive, I want the number, not the charge with it. So example, the number 19, it's CO3 2-. So this is the ion we're looking at. We want to take the magnitude of the charge on that ion. So that's the number 2. We don't want to bring the charge itself though. So when we calculate equivalents per liter, it's never going to be negative. It's always going to be a positive number. So that's why we just want to take the 2 and not the negative with it. So I would take this number 2 and then multiply it by the molarity. So you're always going to be given a molarity in an equivalent per liter problem. And in number 19, it says the molarity is 0.064. Do that right, 0.64. So you get 0.1, or no, 2 sig figs, right?
Okay. Well, so it'd be
1, 3. So the calculation itself isn't that tricky because it's always just, okay, what's the charge multiplied by the molarity? There's never be rearrangements of it or anything. You'll actually see some of these calculations in the healthcare field because ions are important, right? You want to know potassium levels, you want to know sodium levels, and you do a similar calculation when you figure those out. You take the concentration of the sample, whether it's blood, urine, something like that, and you multiply it by the charge on that ion. Potassium would be a +1. Okay, so you would have a 1 here, and then whatever the concentration of those potassium ions in the sample you're looking at. Now, usually in the healthcare field, it's milli equivalents, MEQ, because we're looking at very small amounts, right? It's metric system. So when we're looking at the metric system, we could put equivalents here in that base. And so usually you're looking at the milli equivalents way down here because you're looking at tiny amounts, tiny concentrations. But just to relate it to the healthcare field, because this is the chemistry you take usually when you're pursuing a career in a health field. So that is the last type of concentration calculation for chapter 6. So we're going to look next at chapter 7. There's not a lot of calculations in chapter 7. If you look at the equation sheet itself, there are 3 equations in the next 2 chapters that we're looking at. Okay, so that Q is equal to MC TF minus TI, that's our chapter 7 equation. I think that's the only one. And then the other 2 for pH, which we're going to talk about in chapter 8. So chapter 7, what we're looking at now, chapter 7 is largely definitions and utilizing Le Chatelier's principle. So what we're going to do is we're going to start by looking at that one equation, MC TF minus TI, that we have on our equation sheet for chapter 7. So what is this equation? What do all of these letters mean? So Q is our heat. When we measure heat, what we're going to measure it in is calories. So CAL is the shorthand for the units on heat. So you can kind of think of this even just as a function of your body. When you're trying to burn off calories, you're burning off calories because you're burning off heat. You're warming up your body, you're moving your muscles, burning those calories. Same sort of thing. This is heat energy. Looking at the M, well, M is just mass. And we're going to measure it in grams. So G, grams. C, so this is a new one. We haven't seen this at all, specific heat. So what specific heat is, it's a measure of the heat content of a substance. So for example, depending upon what type of material we're looking at, whether we're looking at water or acetone or a solid like aluminum, they're all going to have different specific heats depending upon the material. Because the definition of specific heat is how much heat is required to make that material move up by 1 degree Celsius. So how much heat do I need to add to it to get its temperature to raise by 1 degree? So aluminum, for instance, is going to have a lower specific heat than water because you can warm up a metal much quicker than you can water, right? Like if you walk outside on a hot day, would you rather step out on a metal deck or on a wooden one? Wood. Wooden, because metal has a lower specific heat. It doesn't take very much heat to raise its temperature. Wood has a higher one. And then water, even higher, right? It takes forever for the pool to get warm when you, even on a hot day, whereas the cement around it is super hot. So that's what specific heat is. Now you're just going to be given these specific heats in the question itself, but I want you to understand where they're coming from. So the units on these are weird. It's, I have to remember, calories per gram degree Celsius. Calories. Kind of a weird one. So calories in the numerator, it goes along with that heat value, grams in degrees Celsius in the denominator. The nice thing about the units on the specific heat though is they remind you of the units on all of the other variables, right? Grams for mass, calories for heat, and then our last 2 variables, degrees Celsius for temperature. So we have a TF, which is final temp, and it's in degrees Celsius. And then we have our TI, which is just the initial temp. All right. So we're going to do a problem using these in a moment. But let's look at number 20, because we just want to go in order on our practice questions. So number 20 is a concept question. It's not a calculation question, but it's going to, this definition of heat is going to help explain this. So it's saying, what is another name for the heat involved in a reaction due to the breaking and formation of bonds. Okay, so it's not this Q value, this is the heat. They're saying, what's another name? So in the video, I talk a little bit about enthalpy. So enthalpy is the heat that goes into breaking bonds. I should say breaking and forming. So I talk a little bit about enthalpy. That's the definition. To calculate enthalpy, we do here. So H represents enthalpy. That's the variable for enthalpy. Now, you're not actually going to be calculating enthalpy. What you're going to get is this change. So if I tell you the change in enthalpy is positive or the change in enthalpy is negative, you're going to be able to use that to tell if a reaction itself is endothermic or exothermic. So those are two new terms in this chapter as well. Okay, so like I said, this chapter is largely definitions. So those PowerPoints, I recommend watching that video. And I show all the definitions, and I give examples to the reaction equations. So this enthalpy is the heat that goes into breaking and forming bonds. So if you have a reaction, for instance, let me just write one out. I'm making this up on the fly, so I apologize in advance. It's usually how I work. So this isn't balanced, but what's happening in this reaction, what type of reaction is it, first of all? Is it synthesis, decomp, single, or double? Double. It's double replacement. But what's happening in this double replacement is in order for them to switch partners, they're going to have to break a bond, right? And form new ones. So in order to break bonds, we need some heat energy. We need some energy to break that bond. It takes energy to break that bond. And that's what enthalpy is. That's the name of that energy that's going into breaking the bond. Now, when new bonds are formed, oftentimes heat's released because they come together and release energy in the form of heat. Okay, so that's enthalpy as well. So it's the heat going into breaking the bonds, and it's the heat that's released. So what we look at when we're calculating this change in enthalpy is, what's my initial enthalpy? So that's the reaction side of the equation. What do I initially need to break these bonds? How much heat do I need to break these bonds? And then your final is going to be your products. Because the initial, what you're starting with, what you're putting in the flask, is the reactants, right? And then what you're getting out of the flask is the products. So that's why it's your final. That's why it's the HF. So you're taking these values and comparing them, or finding the difference between them to get our total change in enthalpy. Now, oftentimes, you'll see, given the reaction equation, that sometimes they'll have a number. So let's say 2.5, and it'll be calories. So what this number is, and it'll say either calories or it'll say kilocalories with a K. Okay? This number is the actual calculated heat that we're doing here. Because calories, calories. So this is how they're related. Okay? This is the heat that's going into breaking the bonds, and this is Q is the actual value. So when we use this equation, which we're going to do here in a moment, what we're calculating is the heat that is going into the reaction. Sometimes we'll see the heat on the reactant side, and sometimes we'll see the heat on the product side. And I'll talk about what that means once we get to a problem like that. But it might be over here, or it might be over here. We're never going to see a Q value, a calorie value on both sides. It'll always be either on the reactant or either on the product. And that will help us figure out if it's endothermic or exothermic as well. Okay. But before we get into endothermic and exothermic, let's see how we actually calculate this value using this equation. Okay, so I'm going to leave this information over here up and erase this so that we can try number 21. So, number 21 is how many calories of heat are produced or absorbed. So produced would be if it's on the product side of the equation. Because if it's produced, it means made, right? If it was absorbed, that means it was on the reactant side because it absorbed heat to make the reaction go further.
Yes.
So we need to figure out whether it was produced or absorbed. So it's saying when ammonium chloride is dissolved in water. So let's look at the actual values they're giving us so we can plug it in and solve. And then we'll talk about if it's endothermic or exothermic. So they give us 80.0 grams of solution. So that 80.0 grams, which variable is that? It's our mass, yep. So that's going to be 80.0 grams. Just write a new list. Actually, might be a little bit easier to see that way. And then they say a temperature change. And they give us two temperatures. Now the key in these two temperatures is we need to figure out which one's the initial and which one's the final. Because if we flip it and mess it up, we might get a positive when we should have got a negative, and that's going to throw everything off. Okay, so between the 25 and the 18, which one of those is the final temperature? 18. They're saying it changed from 25 to 18. So it's lower, yes. It went down, the temperature went down. So that's going to be our T sub F is the 18, and our T sub I is the 25. Assume the specific heat of the solution is 1. So a lot of your specific heats are going to be right around that 1 value because most of our reactions that we talk about are in water. And the specific heat of water is 1. Okay? Just so you're wondering why it's always almost the same every time we have a specific heat. So we're usually talking with water solution. Okay. So we have all the variables, and now we just plug them in. Q equal to mass is 80, we said. Multiply that by C, just 1. And then make sure you're putting the temperature in parentheses because you want to do the subtraction first. So 18 comes first, and we're subtracting 25 from it. So notice we're going to get a negative Q value.
I got 560. Did you get negative 560? Yeah.
Negative 560?
Yes.
How many sig figs? 3.
Oh.
So just put a decimal there to include the 0. And then the units. Calories. That's our heat energy. So, with that value, the question then asks, so that's the answer to how many calories of heat. But next it says, also, is the dissociation of NH4Cl endothermic or exothermic? So let me just write this equation up here so you can kind of see what they mean by dissociation. They're just saying we have this solid ionic compound. It is ionic because NH4 is one of those NH4 plus ions, one of those polyatomics. So since we have ions involved, they're saying once we add water to it, what happens is it's no longer a solid, right? It's now two ions in solution. So we have NH4 plus ions and Cl minus ions in solution. So they're saying when this dissociation happens, heat is either absorbed or released. So we're going to figure out which one. Now, for the endothermic, exothermic, that defines whether it's absorbed or released, produced or absorbed, right? So endothermic, the definition is, in a reaction, the heat is absorbed. So what you're going to notice in an endothermic reaction, if you're holding onto the flask during it, you're going to feel it get colder. So why do you feel it get colder? Because it's absorbing heat. And if your hand's around it, it's going to absorb the heat from your hand. So you will feel it get colder, making the reaction itself get warmer, because it's absorbing heat from your hand. For exothermic then, heat released, if you're holding on to it, you would feel your hand get warmer. Because since it's releasing heat to the surroundings, your surroundings being your hand, you would feel that heat being released. So how to figure out if it's endothermic or exothermic? I like, instead of memorizing, oh, Q value is positive, Q value is negative, I like to look at the temperatures themselves. So the initial was 25. Did it get colder or did it get warmer?
Okay.
It went from 25 to 18.
Oh, the temperature dropped, so it got colder.
The temperature dropped. So if you were holding on to it, would you feel it get colder
Yes.
Yes.
or warmer? You would feel it get colder. So this has to be an endothermic reaction. Because the temperature dropped, you would feel it get colder. So this is endothermic. And another way, if you don't want to look at the temperatures and try to figure that out, if the Q value is negative, it's endothermic. If you actually solve it, you get a negative Q value, it's endothermic. So for exo, your Q value is going to be positive. And you'll see the temperature increase. So we just said it was endothermic, right? Negative 560, endothermic. So that means the heat was absorbed. So if the heat was absorbed, do you think that Q value would go on the reactant side or the product side?
Absorb, so it has to be in the, you take it in, so it's in the first. Yes.
Yep, it has to be in the first. So if it's absorbed, that means that heat needs to be over on the reactant side.
It's not
If it was released,
yes.
another word for released means produced.
Yeah.
Produced products. So in an exothermic reaction, you're going to see the calories, the heat, on the product side. In an endothermic reaction, you're going to see the heat on the reactant side. And oftentimes, they don't even put a value here. They'll just put heat. Because they don't want to calculate the value, they just know it happens to be endothermic, so there's some sort of value over here. So this is example of endothermic. all ties together. Let me also add, so we talked about Q values, endothermic, it's when the Q value is negative. Well, we talked about a minute ago that delta H, the enthalpy. So this is why I don't like to remember the negative positive, but I like to look at the temperatures and figure it out, is because it gets confusing because the Q value is negative, it's endothermic, but if the enthalpy is positive, it's endothermic. They're opposite. So here it would be delta H is negative, it's exothermic. So it depends which one you're calculating. Are you calculating the heat or are you calculating the enthalpy? Right? And we're not ever going to calculate enthalpy, but you might be given the change in enthalpy and have to figure out if it's endothermic or exothermic. So we're just going to look at one more, and we'll talk about Le Chatelier's principle the next time, because that's kind of a big topic. But since we're talking about endothermic and exothermic, number 22 is showing a reaction coordinate diagram, which we can use to figure out if something's endothermic or exothermic. So I'm going to erase this definition so I can draw that diagram, so we can point out the parts of the diagram. So we have so this over here, on this platform, this is our reactants. Okay, whether it be A plus B, or AB plus CD, or whatever. Okay, so this is where the reactants are. The products are on this line over here. So this big hump, this is kind of what's happening in the in-between, which is going to help us figure out if it's endothermic or exothermic. So let me do so this is called the activation energy. So the reason we're drawing this is because if this activation energy is very large, that means the reaction is going to take a long time. It means it's a slow reaction because it has a large hump to come over before it can get to products. If this hump is really small, low activation energy, that means the reaction is going to happen faster because it doesn't have as far high to travel. Okay, so that's what the activation energy tells us, is it can tell us the speed of the reaction, the ease of the reaction. Okay, and that's from where the reactants are to the top of the hump. That's that measurement there. Now this measurement, from the reactants to where the products are, that's my delta H. That's my change in enthalpy. So what is the change in enthalpy going to tell me? It's going to tell me if it's endothermic or exothermic. So I'm looking at the difference here. So how do I figure that out just by looking at this diagram? Well, you'll notice that there's numbers on the side. And you don't even need to know the units or anything like that. We're just going to use the numbers to figure out if this delta H is positive or negative. Because that's all we really need to know. We don't need to know the magnitude of delta H. We need to know the charge of delta H. 40 is like way up here, sorry, but so on and so forth. So, what is the definition of delta H? We said it was the final minus the initial.
It's gonna be 20.
But is it going to be positive or negative? What's our final? Is our final the reactants or is our final the products? The products are the final. That's what we get out at the end of the reaction.
Mm-hmm.
So our HF, let's just estimate what it is.
Yes.
You say it's 20 about? Okay.
Yes.
Our HI, these are going to be the reactants then, right?
The 40.
and they're approximately at 40 right now. So is this going to give you a positive or negative?
Negative.
It's going to get you a negative. So knowing that it's negative tells us whether it's exothermic or endothermic. It has to be exo, because the delta H, if it's negative, which we just calculated it was negative, it's exothermic. So this reaction is exothermic because it had a negative delta H. And so you'll always see a negative delta H when the products are lower in energy than the reactants. So if my products are down here and my reactants are anywhere up here, it's going to be exothermic every time. That's why you don't need to know the numbers itself. You just need to see where they are. For example, if I had, I'm just going to draw a makeshift one, this reaction coordinate diagram. These are my reactants. These are my products. So, looking at this one, my products are higher energy. And I take my products, that HF, minus my reactants. So if my products are higher in energy, I'm going to get a positive delta H. So this is an example of positive delta H, and positive delta H means endo.
Yeah.
So this is always what an exothermic one's going to look like. That activation energy hump might be different, but you're always going to see your reactants higher in energy than your products. Endothermic, you're always going to see your reactants lower in energy than your products. When we come back next class, I'll make a big table summarizing this so you can have it all in one spot. Where, what are the Q values? What does that mean for exo and endo? What are the H values? What does that mean? And then the reaction diagrams as well. You can do the change in temperatures if you want. There's a lot of different ways to figure out if a reaction is endo or exothermic. So, before I end, let's do 23 because this recording it's asking about this diagram. In this reaction diagram, what would adding a catalyst do to the activation energy? So, definition of a catalyst is it tries to speed up the reaction. So, looking at this activation energy, this hump, if I wanted to speed up the reaction, that's what a catalyst does, what would I want to do to the hump?
Make it higher.
So if I make the hump higher, is that going to make the reaction take longer or shorter?
Oh, longer.
Longer. So I'm going to want to decrease it.
Decrease it.
So what a catalyst would do to the activation energy is make it smaller. So it probably make it look more like this. So EA would get smaller or lower EA. So catalysts only affect the activation energy, the speed of the reaction, because they're trying to get the reaction to go faster. So when it says, what effect would a catalyst have on enthalpy? So remember, enthalpy is here. A catalyst affects the speed of the reaction. It's going to do absolutely nothing for enthalpy. It's not going to change where the products or reactants are, it's just going to change the rate of the reaction. So a catalyst does not affect enthalpy. It just affects the rate of the reaction, the activation energy. So that's kind of a trick question there. So we'll leave the Chatelier's principle for next time. That's a completely different set.